In this lecture, we're going to look at homogeneity, which is a very important concept in economics. So let's begin by supposing that y is a function of x1 and x2, so that the profit is given by price times this function minus r1 x1, where r1 is the price of input 1, x1 is the amount of input 1, and also minus r2 x2. So we take the first order conditions, which we do by setting the first derivatives, the first partial derivatives equal to 0, and we get that the price times the marginal product of x1 minus r1 is 0, and that the partial of the profit function with respect to x2 is the same in that the price times the marginal product of x2 minus the input price of 2 is 0. So we get these two results. We get P times marginal product of 1 is equal to the input price of that input, and price times marginal product 2 is equal to the price of input 2. So then if we solve for the price, we get that price is equal to R1 over F1, where F1 is the marginal product of 1, equals R2 over F2, and we can rearrange that by putting 1 over P. So we get then the marginal product of 1 divided by the price of 1 equals the marginal product of 2 divided by the price of 2. And then rearranging, we get this formula in red bracket or in red square, where we get price times the marginal product of 1 over the input of 1, the input price of 1 equals price times marginal product of 2 over the input price of 2, and that's all equal to 1. Now the price times the marginal product of any input I is simply equal to the marginal value product. Okay, the marginal value product. And what we have along any expansion path, so along any expansion path, we would find that we have this condition, that the value of the marginal product divided by the input price of one good is equal to the value of the marginal product divided by the input price of another good, and that in equilibrium, if profit is maximized, it's equal to 1. If profit is not maximized, we get a different result in that we retain this equation, this equality, but we may have to give up this one. So we can't reach the optimorum, if you like, where the profit is maximized. So for example, if we had a restriction on the amount of input 2 that's available, we want to stay on the expansion path, but we will not be able to meet this particular equality constraint. All right, so when we look at this in a diagram where we have some input I on the horizontal axis and dollars on the vertical, this downward sloping line is our value of marginal product. And that has to equal the input price, which we assume to be fixed in perfect competition, and then xi star is the optimal amount of the good or the input that we employ. For constant returns to scale production, the sum of the factor payments will equal the value of total output, so that if we have Ri, so the input of I equals the price times the marginal product of I, then if we multiply both sides by xi, we get Ri xi, which is the amount we pay for factor xi, and that's equal to the value of the marginal product times the amount of that input that we employ. So if we take two factors and we look at the total payments, we get R1 x1 plus R2 x2 is equal to, and now we substitute this for here. So we get for input 1, we get that the price times the marginal product of 1 times the amount of 1 plus the price times the marginal product of 2 times the amount of input 2 is equal to, and we take out the price, and we get F1 X1 plus F2 X2, and that has to equal the price of the output. This is also the price of the output times the amount of the output, and the amount of the output is given by this linearity. But remember, we're talking about constant returns to scale. Because it is constant returns to scale, that implies that if each input is increased by proportion k, total output will increase by the same proportion k. So in other words, if we take some function, some production function, which is a function of x1, x2, xn, and we multiply each of the amount of the input that we use by k, then this is equivalent to multiplying the output itself, which is given by f x1, x2 to xn. It's the same as multiplying that output by k. So if all inputs are doubled, output doubles. So if all inputs are doubled, output doubles, and that implies that the production function is homogeneous of degree 1. So in other words, if all the inputs are doubled, we're going to get an increase in output as well, double the output, which implies that the production function is homogeneous of degree 1. So we can define a function f of x1 to xn as being homogeneous of degree r if and only if, when we multiply each of the inputs by k, so we increase the amount of each input by k, then this is equivalent to multiplying the output, total output, which is given by this function here, by k to the power r. If r is greater than 1, we get increasing returns to scale. If r is less than 1, but of course greater than 0, we get decreasing returns to scale. And if r is 1, then we're back up here with constant returns to scale, and it's homogeneous of degree 1. So let's consider first off a production function where production is a function of labor and capital, and we have that the output is equal to the amount of labor employed to the power alpha, and capital employed to the power 1 minus alpha. So if we multiply labor and capital by t, so we increase the amount of labor and the amount of capital by a factor t, then we have TL all to the power alpha and TK all to the power 1 minus alpha, which gives us T alpha T1 minus alpha times the old production function y, and T alpha times T to the 1 minus alpha is simply T. So in other words, we've increased output by a factor T as well. So we've increased all of the inputs by each of the inputs by a factor of T, and that increases output by a factor of T as well. Now consider a demand function, where demand is a function of all the prices that affect it. These are the prices of itself, wherever that I is, and of complements and substitutes, and of course the budget. And if we multiply prices by K and the budget by K, so let's say our prices go up by 10% and our income goes up by 10%. Well, it turns out that our demand for that particular good I does not change. So K equals 0, K to the power 0. So what we have is a homogeneous of degree 0 function. That equal sign should not have been there. Okay, so the demand function then is homogeneous of degree 0. Only relative and not absolute price changes matter. For any homogeneous of degree 0 function, we find that when we have k in here, multiply each of our inputs by k, or it could also be a demand function, then it's as if output does not change at all, or demand in this case does not change at all. Since it holds for any k, if this is the case, if this is true, if it holds for any k, we can choose k being 1 over x1, and we can take that homogeneous of degree 0 function and divide by, multiply by k, but that means divide by 1 over x1. We get a 1 here, and each of the inputs is multiplied by k, so in other words divided by x1, and that's equivalent to some function which is a function of each of the inputs divided by x1. So for example, if the production function as a function of labor and capital is homogeneous of degree 0, this implies that we can write this as F1 K over L, the ratio of capital over labor, and we can write that simply as F of kappa, where kappa is the capital per worker. We also have a theorem here that if a function x1 to xn is homogeneous of degree r, then the first partial derivatives are homogeneous of degree r minus 1. And we can prove that by starting with multiplying each of the individual values in the production function, variables in the production function, or any function for that matter, by k, and we get that k to the r is multiplied by the original function, where r indicates the degree of homogeneity. Then taking the partial derivative of that first function with respect to any k multiplied by xi, and then take multiply that by the partial of kxi over xi, so the partial of kxi with respect to xi, and we get kr multiplied by the partial of f over dxi, which is simply the marginal product in the case of production. So then we can rearrange that, because when you take this derivative, you can see automatically that it's k. So we get the partial of f with respect to kxi times k is equal to kr times the partial of df dxi. So we bring the k to the other side, and that's like subtracting a k, dividing by it. In other words, it's like subtracting a 1 from the exponent, and we get that the partial of f with respect to kxi is equal to kr to the minus 1 partial of f with respect to dxi. So the function fi evaluated at kx1 ... kxn equals k to the r minus 1 derivative of the original function with respect to one of the inputs. So that's the proof that we have an original function that's homogeneous of degree r, is then its first partials are homogeneous of degree r minus 1. For a linear homogeneous production function, the marginal products are homogeneous of degree 0. Recall this expression here, that the slope of some level curve is equal to minus f1 over f2, where the 1 and the 2 refer to the partial derivative of that function with respect to input 1 and input 2. So homogeneity of any degree implies that the slopes of the level curves of the function are unchanged along any ray through the origin. This is illustrated in the following diagram. So you'll see here we have a ray through the origin. We have input x1 and input x2. These are our isoquants. And along that ray, the isoquants all have the same slope. Okay, the slope of this is equal to the slope of that, slope of that. And if you pick any other ray through here, you'd get exactly the same thing. Those slopes would be the same in each case. So what that implies is that if you have x1 naught and you increase it to kx1 naught, then your output or your other input goes x2 naught to kx2 naught, and you've basically increased x2 and x1 by k, and you keep the same slope, although you jump to a higher isoquant. So we refer to these curves as being, the level curves are radial expansions of one another, and that's the characteristic that the function is homothetic. So let y equals f of x1 to xn be homogeneous of degree r, and let z be a function f, capital F, that acts on y. So y is an input into it. And assume that that first derivative of that function f with respect to y is greater than 0. This implies that f is a monotonic transformation of y. Then z is a homothetic function as indicated in that diagram above. All right, so that's how we characterize a homothetic function. Now, an important theorem in economics is Euler's theorem. Suppose that f is a function of various inputs x1 to xn, and suppose that that function is homogeneous of degree r. Then, if we take the partials of the function with respect to each of the parameters of the function, x1, x2, xn, and for each of those we multiply it by the level of the input, or the function, the variable in the function, the independent variables. Then if we sum those partial derivatives of x's with times the levels, then we get a function r, or a parameter r, times f x1 to xn. So the original function is multiplied by r, and r is the degree of homogeneity. And this holds, this triple equality, if you like, indicates that it holds for all xi. Now we want to prove that, and we do so by the definition of homogeneity. So f, if each of the inputs into f is multiplied by k, we get k to the r, where r is the degree of homogeneity, and f again is the original function. We differentiate both sides with respect to x, so derivative of f, we differentiate both sides with respect to k, and the partial of f with respect to kx1, and then the partial of kx1 with respect to k, and we do the same thing for each of these. So for the last one, we have the partial of f with respect to kxn multiplied by partial of kxn with respect to k, and that's equal to, because we're differentiating both sides, with respect to k is equal to r times k, r to the minus 1 times the original function here. All right, then we can rearrange that by solving these partial derivatives with respect to k, and they're equal to k x1 and x2, x3 up to xn, and before each of those we have the partial of the function with respect to k x1, with respect to k x2 and xn, and these are all summed, and that again is equal to r times k to the r minus 1 times the original function. Since this holds for r for all k, let k be 1. So in that case we get back to these partial of f with respect to x1 times x1 plus partial of f with respect to x2 times x2, and so on until the partial of f with respect to xn times xn is simply equal to r times the original function. That then proves that we have the sum of all these partials of the original function times their levels is equal to r times the original function. Now this is important because for linearly homogeneous functions, r is equal to 1, and that says that if I take the marginal product of x1, multiply it by x1, and add to it the marginal product of x2 times x2, and so on until the final one, whatever the inputs are, the marginal product of input n times xn, that exhausts the total output. So Euler's theorem says that for constant returns to scale production, the sum of the marginal products of each factor times the level of factor use exactly adds up to total output. And that's important in economic theory. It also says that if r is equal to 0, so homogeneity of degree 0, then the sum of the marginal products times xi equals 0. And finally, we want to just review the functions of functions, where we consider a utility function, say f of x and y, where x and y are not independent, but x is a function of t, and y is a function of t. X is a function g of t, y a function h of t. Then the total derivative of the utility function with respect to t is given by du dt equal to partial of u with respect to x times dx over dt plus the partial of u with respect to y times dy over dt, which is equal to the first derivative of f with respect to x, which is our marginal utility in this case, times dg dt plus marginal utility of y times dh dt. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.